void paradox.
Why empty space is the universe's deepest secret. In 1998, astronomer Robert Williams pointed the Hubble Space Telescope at a patch of sky so empty, so utterly devoid of visible objects, that many astronomers thought he was wasting precious telescope time. The region near the Big Dipper appeared completely black. No stars, no galaxies, nothing. Ground-based telescopes had surveyed it countless times and found it empty. Williams exposed Hubble's sensors to this nothing for 10 days, 342 consecutive orbits, the longest exposure in the telescope's history at that time. When the data came back, astronomers couldn't believe what they were seeing. That empty patch of sky, that apparent void, contained approximately 3,000 galaxies. Every single point of light in the image was an entire galaxy containing hundreds of billions of stars. And this was from a region of sky smaller than a grain of sand held at arm's length. The Hubble Deep Field image revealed something disturbing. There is no such thing as empty space. Everywhere we look, no matter how dark and vacant it appears, we find the universe is full. But that's just the beginning of the paradox, because when physicists examine what fills that space, when they look at what exists between the galaxies, between the stars, between the atoms, they find something even stranger. The vacuum of space, the void between matter, isn't empty. It's seething with activity. It contains energy. It exerts pressure. It bends space-time. It might contain more mass energy than all the visible matter in the universe combined, and we have absolutely no idea what it is. We call it vacuum energy, or dark energy, or the cosmological constant, but these are just names for our ignorance, placeholder labels for something that constitutes 68% of the universe but remains completely unexplained by physics. Empty space isn't empty. It's full of something we can't detect, can't understand, and can't eliminate even in principle. Today, we descend into the void, exploring what nothing really means, why empty space might be the most important substance in existence, and why understanding the void is the key to understanding reality itself. Pause. What you're about to discover will transform nothing into the most fascinating thing you've ever contemplated.
It's to an abyss of mystery. When you remove everything from a region of space, every particle, every photon, every quantum of energy, what remains? The answer, as we'll discover, is not nothing. It's something far stranger. Let's explore the void. Act 1. The impossibility of nothing. The ancient Greek philosopher Parmenides argued around 500 BCE that nothing cannot exist, because if it existed, it would be something, not nothing. For 2,000 years, this seemed like philosophical word games. Of course nothing exists. The vacuum of space, the absence of matter, the void. But in the 20th century, physics proved Parmenides was right. Nothing, true, absolute nothingness, is impossible. The laws of quantum mechanics forbid it. Here's why. According to Heisenberg's uncertainty principle, you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. But this principle isn't just about measurement limitations, it's about the fundamental nature of reality. Particles don't have precise positions and momenta simultaneously. These properties are intrinsically uncertain. Now, apply this to empty space. If you want to create a region of perfect vacuum, absolutely nothing, you would need to remove all particles. But that means the momentum of particles in that region would be precisely zero. And if momentum is precisely zero, then by the uncertainty principle, the position becomes infinitely uncertain. which means particles could appear anywhere at any time. In other words, the moment you try to create perfect emptiness, quantum mechanics guarantees that particles will pop into existence to fill it. This isn't theoretical speculation, it's been observed directly. In 1948, Hendrik Casimir predicted that if you place two metal plates very close together in a vacuum, the empty space between them would exert a force pushing the plates together. The reason? The vacuum isn't empty, it's filled with quantum fluctuations, virtual particles constantly appearing and disappearing. Between the plates, only certain wavelengths of these fluctuations can fit. Outside the plates, all wavelengths exist. This creates a pressure imbalance, more quantum activity outside than inside. The plates get pushed together by nothing, or rather, by different types of nothing.
The Casimir effect was experimentally confirmed in 1997. Researchers at Los Alamos measured the force between gold-coated plates separated by less than a micrometer. The force matched Casimir's predictions exactly. Empty space exerts measurable physical force. Nothing pushes atoms around. The vacuum has structure, properties, dynamics. It's a something, not a nothing. But it gets stranger. When physicists calculate how much energy should exist in empty space due to quantum fluctuations, they get an answer that's spectacularly, embarrassingly wrong. Here's the calculation. Every quantum field, electromagnetic, electron, quark, etc., contributes energy fluctuations to the vacuum. Add them all up across all possible wavelengths up to the Planck scale, the smallest meaningful distance in physics, and you get 10 to the 94th grams per cubic centimeter. That's a 1 followed by 94 zeros. That much mass energy in every cubic centimeter of space, in a volume smaller than a sugar cube. If this were true, the universe would be extraordinarily different from what we observed. The vacuum energy would be so dense that space-time would curl up into a tiny ball. Stars, galaxies, atoms, none could form. Space itself would collapse or explode instantly. But we observe something very different. The universe exists. It's mostly flat. It's expanding, but not catastrophically. When cosmologists measure the actual vacuum energy density by observing the universe's expansion rate, they find approximately 10 to the minus 29 grams per cubic centimeter. The theoretical prediction is 10 to the 123 times larger than observation. This is called the cosmological constant problem, and it's the worst prediction in the history of physics, wrong by 123 orders of magnitude. Something is canceling out the vacuum energy, almost perfectly, but not quite. If the cancellation were perfect, vacuum energy would be exactly zero. But it's not zero. It's a tiny positive number. And that tiny number is having profound effects on the fate of the universe. This leftover vacuum energy, what we call dark energy, is causing the universe's expansion to accelerate. Galaxies are flying apart faster and faster, driven by the repulsive pressure of empty space. Eventually, in hundreds of billions of years, this acceleration will tear apart galaxy clusters, then galaxies, then solar systems, possibly even atoms. The universe will end in what cosmologists call the Big Rip, reality torn apart by the expanding void. All of this raises a disturbing question. What is the vacuum? What is this thing we call empty space? The traditional view, dating back to Newton, is that space is a passive stage where physical events unfold. It's the background, the container, the arena. It doesn't do anything, it just provides the where and when for matter and energy to interact. But modern physics reveals something different. Space is dynamic, active, substantial. It has energy. It can curve, stretch, vibrate. It can give birth to particles and swallow them again. It's not a stage, it's an actor, perhaps the most important actor in the cosmic drama. Consider black holes. When a massive star collapses, it doesn't just compress matter to incredible density, it warps space itself so severely that a region forms where space curves in on itself, the event horizon. What exists inside the event horizon? You might think matter compressed to a singularity, but that's not quite right. The matter that formed the black hole fell toward the center, and then what? According to general relativity, the matter reaches the singularity, a point where space-time curvature becomes infinite, in finite time from the matter's perspective. But from an outside perspective, the matter never actually reaches the singularity. It's frozen at the event horizon forever.
So what's inside a black hole? Mostly space. Incredibly warped space. Space where the geometry is so extreme that time and space swap roles, where the center is not a place but a moment in time, your future inevitably approaching. The black hole is made of void, shaped void, structured void, void so curved that it becomes its own prison. Nothing has never been so substantial. And then there's the phenomenon called vacuum decay, one of the most terrifying theoretical predictions in physics. Our vacuum, the quantum vacuum with its particular energy density and field configurations, might not be the most stable possible vacuum. It might be a false vacuum, temporarily stable, but capable of decaying to a lower energy true vacuum. If this decay happens somewhere, triggered by a quantum fluctuation or high-energy collision, it would create a bubble of true vacuum expanding at the speed of light. Inside the bubble, the laws of physics would be different. Particles would have different masses, forces would have different strengths. Atoms as we know them couldn't exist. The bubble would consume everything in its path, rewriting the rules of reality as it expands, unstoppable and eternal. This is vacuum decay, the possibility that the void itself is metastable, and that nothing could suddenly transform into a different kind of nothing that destroys everything. We don't know if our vacuum is metastable. We don't know how likely vacuum decay is. We don't know if it's already happened in distant parts of the universe, with death bubbles racing toward us at light speed. The void might be safe, or it might be a loaded gun pointed at all of existence, waiting for the quantum fluctuation that pulls the trigger. All of this from studying nothing, from trying to understand what exists when nothing exists. The void is not empty, it's not passive, it's not safe, it's not simple. It's one of the deepest mysteries in physics and possibly the key to everything else. Because if we can understand what the vacuum really is, we might finally understand why the universe exists at all, why it has the properties it does, and what came before the Big Bang. The void holds secrets, and we're just beginning to excavate them.
Act 2. The Structure of Emptiness. Part A. Quantum Foam and the Planck Scale. In the 1950s, physicist John Wheeler calculated what space should look like if you could zoom in to the smallest possible scales, distances around 10 to the minus 35 meters, called the Planck length. At these scales, quantum uncertainty becomes so extreme that space-time itself fluctuates wildly. Space and time lose their smoothness, becoming a chaotic, foaming sea of quantum geometry. Wheeler called it quantum foam. Space-time at its smallest scales is not smooth and continuous, but granular, turbulent, constantly changing. Imagine the ocean's surface from an airplane. It looks smooth, flat, almost featureless. But zoom in closer, descend toward the water, and you see waves, ripples, foam. get close enough and the surface is violently chaotic, spraying water in every direction, impossible to predict. Space-time is like that, smooth at large scales, foaming chaos at the Planck scale. At the quantum foam level, the very concepts of distance and duration break down. A Planck length is the smallest distance that has physical meaning. Try to measure anything smaller, and quantum uncertainty makes the measurement meaningless. Similarly, the Planck time, about 10 to the minus 43 seconds, is the shortest possible duration. Nothing can happen faster. This means space-time has a fundamental granularity. It's not infinitely divisible. There's a smallest unit of space and time, like pixels in an image or frames in a video. But unlike pixels, which are static, Planck-scale space-time is dynamically fluctuating. Virtual black holes pop in and out of existence. Wormholes connect distant regions for fleeting instants. The topology of space itself, its connectivity, its dimensionality fluctuates. This quantum foam is everywhere. Right now, at every point in space, including the space you occupy, there's this seething activity at scales far too small to observe. You're sitting in quantum foam. You're made of quantum foam. Every atom in your body is a relatively stable pattern in the foam, like a persistent whirlpool in turbulent water. The void isn't passive background. It's the fundamental substance of reality, and it's incredibly active.
But here's a mystery that keeps physicists awake at night. We've never directly observed quantum foam. Our best theories, quantum mechanics and general relativity, predict it must exist. The math is clear, but we've never seen it because it exists at scales 10 to the 20 times smaller than anything we can probe with particle accelerators. To directly observe Planck-scale physics, you'd need a particle collider the size of the entire galaxy. We're not building that anytime soon. So, quantum foam remains theoretical, strongly predicted, never confirmed. Yet its effects might be detectable indirectly. One possibility, if space-time is fundamentally granular, then light traveling vast distances might be affected by this granularity. Imagine light as a wave propagating across the ocean. If the ocean's surface is perfectly smooth, all wavelengths travel at the same speed. But if the surface is choppy, with structure at small scales, then different wavelengths might travel slightly different speeds. Similarly, if space-time has Planck-scale structure, different colors of light might travel at infinitesimally different speeds. Over cosmic distances, billions of light years, this tiny difference could accumulate into a measurable effect. In 2009, the Fermi Gamma-Ray Space Telescope observed a gamma-ray burst from 7.3 billion light-years away. If quantum foam affects light propagation, the highest energy photons should arrive slightly later than lower energy photons. They didn't. They arrived simultaneously, within milliseconds, despite traveling for 7.3 billion years. This null result doesn't disprove quantum foam, it just constrains what form it can take. If quantum foam exists, it must be more subtle than the simplest models predict. Or perhaps we're looking for it in the wrong way. Perhaps quantum foam's effects appear not in light propagation, but in vacuum energy, in particle masses, in the values of fundamental constants. Perhaps the vacuum structure is encoded in every property of nature, hiding in plain sight, too fundamental for us to recognize. The void keeps its secrets, but we're developing tools to interrogate it more deeply. Part B: The Vacuum Catastrophe and Fine-Tuning. Let's return to the cosmological constant problem, the 123 orders of magnitude discrepancy between predicted and observed vacuum energy. This isn't just an embarrassing wrong prediction, it's a cosmic mystery that might hold the key to understanding why the universe exists at all. Here's the puzzle. Why is the vacuum energy so close to zero, but not exactly zero? If it were much larger, say even 10 to the minus 120 instead of 10 to the minus 123, the universe would be completely different. If vacuum energy were larger in the negative direction, attractive, the universe would have collapsed milliseconds after the Big Bang. If it were larger in the positive direction, repulsive, matter could never clump together to form stars and galaxies. The vacuum energy is fine-tuned to a precision of 1 in 10 to the 123, like balancing a pencil on its point, but the point is 10 to the 100 times sharper than an atom, and it has to stay balanced for 13.8 billion years. Why? How? 3 main answers have been proposed, and each is strange in its own way. 1. The multiverse explanation. Perhaps there are countless universes, 10 to the 500 or more, as string theory suggests, each with different vacuum energy. We find ourselves in one of the rare universes where vacuum energy happens to be small enough for life, because we couldn't exist anywhere else. This is the anthropic principle. We observe this universe not because it's special, but because universes with different properties don't produce observers. It's logically sound, but philosophically unsatisfying. It explains fine-tuning by invoking infinite unobservable universes. And it raises the question, why do those universes exist? What generates the multiverse? 2. The symmetry cancellation explanation. Perhaps there's a hidden symmetry, a principle we haven't discovered yet, that forces vacuum energy to be precisely zero or near zero. Something like supersymmetry, where every particle has a superpartner with opposite vacuum energy contribution, canceling out the huge quantum fluctuations. The problem? We've searched for supersymmetry at the Large Hadron Collider and found nothing. If supersymmetry exists, it's not the simple, elegant form we hoped for. It's broken, hidden, or more complex than our theories predict. 3. The evolving vacuum explanation. Perhaps vacuum energy isn't constant. Perhaps it evolves over cosmic time, driven by some dynamical field called quintessence that's slowly changing. If vacuum energy was larger in the past and is decreasing towards zero, we might just happen to live at the epoch where it's small but non-zero. Give it a few trillion more years and it might reach zero or become negative. This would mean the void is aging, that nothing itself has a history, an evolution, a future different from its past.
Each explanation requires something strange, unobservable universes, hidden symmetries, or dynamic nothingness. We don't know which, if any, is correct, but all 3 point to the same conclusion: the vacuum is not simple. It's not fundamental. It's structured, perhaps contingent, possibly tunable. Nothing is complicated. And then there's the deepest question of all. Why is there vacuum energy at all? Why isn't it exactly zero? A perfectly zero vacuum energy would be the simplest option. No mysterious fine-tuning, no dark energy, no accelerating expansion, just matter and gravity, straightforward physics. But that's not what we observe. The vacuum has energy, small but definitely non-zero. Some physicists speculate that exactly zero would be unstable, that quantum mechanics requires vacuum energy to fluctuate around some non-zero value. Zero would be a knife-edge balance, infinitely unlikely. A small non-zero value is more generic, more likely by random selection. Others suggest something more profound,
Perhaps the universe's existence requires non-zero vacuum energy. Perhaps reality can only bootstrap itself into existence if the void has structure, energy, dynamics. Perhaps something from nothing is impossible, and the Big Bang wasn't creation from absolute nothingness, but transition from one type of vacuum, pre-Big Bang, higher energy, unstable, to another type, our universe, lower energy, more stable. The void might not be where the universe exists. The void might be what the universe is, structured quantum vacuum in a temporarily stable configuration, evolving slowly towards some final state we can only guess at. We've been taught to think of matter and energy as real, and vacuum as their absence, the background on which reality is painted. But physics suggests the opposite. The vacuum is the canvas, the ink, and the artist. Matter and energy are just wrinkles, ripples, patterns in the void. We're not things existing in emptiness. We're structures made of nothing, temporary organizations of vacuum fields, persistently configured in ways that process information, move through space, and wonder about their own existence. You are the void, complexified, and the void is you, simplified. There is no difference.
Act 3. What fills the void? Part A. Dark energy and the expanding void. In 1998, the same year the Hubble Deep Field showed that empty sky is full of galaxies, two teams of astronomers made another discovery that revolutionized cosmology. They were measuring the distances to Type 1a supernovae, stellar explosions that always reach the same peak brightness, making them perfect cosmic yardsticks. By comparing the supernovae's apparent brightness with their actual brightness, astronomers could determine their distance, and by measuring their redshift, how much their light had been stretched by cosmic expansion, they could determine when the light was emitted. The expectation was that the universe's expansion should be slowing down due to gravity, galaxies attracting each other, gradually decelerating the expansion that began with the Big Bang. But the distant supernovae appeared dimmer than expected, meaning they were farther away than they should be. The universe's expansion wasn't slowing down, it was speeding up. Something was pushing the universe apart, an anti-gravity force permeating all of space, growing stronger as space expands. We call it dark energy, and it comprises 68% of the universe's total mass energy content, more than dark matter, 27%, and normal matter, 5% combined. Dark energy is the vacuum's repulsive pressure, the cosmological constant that Einstein introduced in 1917, then rejected as his greatest blunder, now resurrected by observation. It's the energy of empty space itself. Every cubic meter of vacuum contains a tiny amount of energy that doesn't dilute as the universe expands. As space grows, more vacuum is created, and with it, more dark energy. This creates a feedback loop. Dark energy causes expansion. Expansion creates more space. More space means more dark energy, which causes faster expansion, which creates even more space. The universe is accelerating toward a cold, dark, infinitely diluted future.
In approximately 100 billion years, the acceleration will have pushed distant galaxy clusters beyond our cosmic horizon, the boundary beyond which light can never reach us because space is expanding faster than light can travel. Future astronomers, if any civilization survives that long, will look at the sky and see only their local galaxy group. Everything else will have disappeared beyond the horizon, its light red-shifted to infinite wavelength, unreachable forever. They'll observe an empty universe, just one galaxy in an endless void.
They won't be able to discover cosmic expansion, the Big Bang, or dark energy because all the evidence will have disappeared beyond the horizon. They'll live in a universe that appears eternal, unchanging, and nearly empty, ignorant of the vast cosmos that once surrounded them. We live in a special epoch, late enough for galaxies and stars to have formed, early enough that distant galaxies remain visible. We can study the universe's history, measure its expansion, discover dark energy. In a sense, the void is temporary transparency. Right now, emptiness lets us see through it to distant structures. But eventually, the void will become truly empty, not by removing what's there, but by expanding so much that everything becomes unreachably distant. The void is growing, and as it grows, it becomes more powerful, more dominant, more inevitable. Unless something stops it. Some physicists speculate that dark energy might not be constant. Perhaps it's decreasing, and the acceleration will eventually reverse. Or perhaps it's increasing, and the universe will end in a big rip, torn apart when vacuum energy becomes so intense that it overcomes atomic forces. We don't know. We're observing the void's behavior over just a few decades. We're trying to predict its evolution over trillions of years. It's like watching water freeze for 1 second and trying to predict what ice does over millennia. The void holds its secrets, and time will reveal them, slowly, inevitably, as the universe expands into its own unknown future.
Part B. What exists before space? Here's the most mind-bending question in cosmology. What existed before the Big Bang? The standard answer is nothing. Time itself began at the Big Bang. There is no before. This seems like a conversation ender. If time began at the Big Bang, asking what came before is like asking what's north of the North Pole, a nonsensical question based on category error. But physicists aren't satisfied with that answer, because if the Big Bang created space-time from nothing, we need to understand what nothing means in that context. One possibility, the quantum vacuum. Perhaps before the Big Bang, there was vacuum. Not the vacuum of our universe, filled with quantum fields and virtual particles, but a more primordial vacuum, a pre-vacuum with different properties, different symmetries, different physics. In this view, the Big Bang was a phase transition, like water turning to ice, where the pre-vacuum decayed into our vacuum. The energy released in this transition became the matter and radiation filling our universe. Before the Big Bang, pre-vacuum, symmetric, high energy, unstable. After the Big Bang, our vacuum, broken symmetry, lower energy, temporarily stable. This explains why the Big Bang released so much energy. It wasn't creation from absolute nothing, but conversion from one form of vacuum to another, releasing the energy difference. It also explains cosmic expansion, the brief period of exponential expansion in the first 10 to the minus 35 seconds. The pre-vacuum had enormous energy. As it decayed, that energy drove incredibly rapid expansion before settling into the slower expansion we observe today. But this just pushes the question back. Where did the pre-vacuum come from? And why did it decay precisely when and how it did to produce our universe? String theory offers a speculative answer, the landscape of possible vacua. In string theory, there are approximately 10 to the 500 different possible vacuum states, different ways the extra dimensions can curl up, different configurations of quantum fields. Each vacuum state defines a different universe with different physical laws. Perhaps the pre-vacuum was one of these states. Perhaps it was unstable and decayed into our vacuum. Perhaps there are countless other universes, other bubbles, each with its own vacuum, its own physics, its own history. The multiverse of vacua, Infinite nothings, each slightly different, each generating its own cosmos. But even this has limits. The landscape of vacua exists in something, a mathematical structure, a metaspace where different vacua can nucleate and evolve. What is that? What's the ultimate ground of existence, the thing that needs no explanation, that simply is? Some physicists argue it's mathematics itself, not equations written on paper, but abstract mathematical structures that exist platonically, independent of physical instantiation. The universe exists because it's a mathematical structure. The vacuum exists because it's the simplest stable solution to quantum field equations. There's no creation, just timeless mathematical existence. Others argue for a radical possibility. Reality is computational. The universe is a vast quantum computation running on something. The vacuum is the computational substrate, the hardware on which the software of physics runs. What runs the computation? Perhaps consciousness, not human consciousness, but something more fundamental. Perhaps awareness is the ground of being, and matter, space, time, even vacuum are structures within consciousness. This view, called idealism or panpsychism, seems mystical, but it's gaining traction among some physicists and philosophers as traditional materialism struggles to explain consciousness and quantum mechanics. We don't know which, if any, of these views is correct. We might never know. The ultimate origin might be forever beyond empirical investigation. But all these possibilities share one insight. Existence is inevitable. Something must exist because absolute nothing is impossible, forbidden by logic, by quantum mechanics, by mathematics itself. The universe exists because non-existence is incoherent. The void exists because emptiness cannot be empty. We exist because nothing is impossible.
Act 4. Living in the void. Let's bring this back to human scale. What does all this quantum foam, vacuum energy, dark energy, pre-Big Bang vacua mean for your daily existence? More than you might think. First, you are mostly empty space. If you compressed all the matter in your body, removed all the empty space between and within atoms, you'd fit into a cube smaller than a grain of sugar. The vast majority of your volume is void. But that void isn't nothing. It's quantum fields holding you together. It's electromagnetic force keeping electrons around nuclei. It's the structure of space itself, curved by your mass, permeated by your energy. You are a pattern in the void, a complex, temporary organization of nothingness. Second, the void connects you to everything. Quantum fields permeate all of space. The electromagnetic field in your body is continuous with the electromagnetic field everywhere else, in the air, in the earth, in the sun, across the cosmos. You're not separate from the universe. You're a localized excitation in its fields, like a wave in an ocean, made of ocean, never separate from ocean. When you move your hand, you disturb quantum fields. Those disturbances propagate outward at light speed as electromagnetic radiation. Your motion affects the entire universe, infinitesimally, yes, but truly. The void transmits your influence everywhere. You touch the cosmos through the void. Third, the void gives you possibilities. In a completely full universe, no empty space, matter packed solid, you couldn't move, couldn't change, couldn't think. Thought requires neurons firing, chemicals flowing, electrons shifting, all requiring empty space for matter to move through. The void is what makes change possible. It's the space of potential where new patterns can form, where old patterns can dissolve, where possibility becomes actuality. You exist not despite the void, but because of it.
The emptiness between your atoms is as essential to your existence as the atoms themselves.
Fourth, the void might be conscious. This is speculative, controversial, but worth considering. If consciousness is a fundamental feature of reality, if awareness is somehow built into quantum fields or space-time itself, then the void isn't just unconscious substrate, it's the ground of consciousness. Your awareness isn't generated by neurons alone, but by the quantum fields those neurons disturb, the vacuum states they occupy, the information patterns they create in the structure of space. You might not be consciousness in the void. You might be the void's way of being conscious, reality experiencing itself through the pattern you call me. Fifth, the void has a future, and so do you. In 100 billion years, the accelerating expansion driven by dark energy will have pushed everything beyond visibility. In 1 trillion years, star formation will cease. In 10 to the 100 years, black holes will evaporate. Eventually, in timescales almost meaningless in their vastness, the universe will be cold, dark, dilute, quantum fluctuations in an ever-expanding void. But quantum fluctuations mean possibility. Given infinite time, those fluctuations will eventually create new structures, new complexities, maybe even new forms of life and consciousness. The void is patient. It has eternity. And in eternity, everything possible eventually occurs.
The far future is terrifying. Our sun will die. Our galaxy will darken. The universe will cool toward absolute zero. But it's also hopeful because the void persists. Quantum fields continue existing. Vacuum energy endures. The universe remains forever a place where things can happen. As long as the void exists and it seems eternal, possibility exists. And with possibility comes hope. We began by asking, what is nothing? The answer, nothing is everything. Nothing is the foundation of reality. Nothing is full of potential, structured by quantum mechanics, governed by physical law, connected across all space, evolving through all time. Nothing is not the absence of something. Nothing is the presence of everything in its most fundamental form. You are made of nothing. You live in nothing. You will return to nothing. But that nothing is magnificent, complex, dynamic, eternal, and creative. The void is not your enemy, it's your home, and it's been waiting for you for 13.8 billion years to wake up and realize what you are.
Now concluding. We explored the void, from quantum foam at the Planck scale to cosmic voids spanning billions of light years. We discovered that empty space isn't empty, that vacuum has energy, that nothing has structure. We learned that the void preceded matter, that it might outlast matter, that it connects everything through quantum fields and curved space-time. We encountered the mysteries, the cosmological constant problem, the nature of dark energy, the origin of vacuum energy, that remain unsolved despite decades of research. And we glimpsed possibilities, the multiverse of vacua, consciousness as ground of being, the eternal recurrence of quantum fluctuations that challenge everything we thought we knew about existence. The most profound realization is this: the void is not absence, it's presence. When you look at empty space, between stars, between atoms, between thoughts, you're not seeing nothing. You're seeing reality in its purest form, undisturbed, uncluttered, pregnant with possibility. The void is where everything comes from and where everything returns. It's Alpha and Omega, beginning and end, the eternal now that contains all moments. You cannot escape the void. It surrounds you, fills you, constitutes you, but you don't need to escape it, because the void is not hostile, it's not cold, it's not empty. It's the warmth of quantum energy, the connection of entangled fields, the potential of infinite possibility. It's home, your true home, the place you've always been and will always be. Physics is still excavating the void's secrets. Every experiment, every observation, every theory brings us closer to understanding what nothing really is. But perhaps the deepest understanding isn't scientific, it's experiential. You know the void intimately. Every time you close your eyes and experience the darkness behind your eyelids, every time you pause between thoughts and notice the silence, every time you rest in awareness itself, without content, without object, you're experiencing the void. Not nothingness, but pure presence. Not absence, but the background against which all things appear. The universe is vast. The mysteries are endless. The void is eternal. But you are not separate from any of it. You are the void, temporarily believing itself to be something other than void. You are nothing, magnificently disguised as something. And when you finally return to the void, as you inevitably will, you won't be lost. You'll be home.